Welcome to Shanti-Peace for Mathematics. In this video, we'll discuss a Leibniz rule or a Leibniz theorem, which is known as a product rule for successive derivatives. So let us understand what is the rule is. So if u and v are two functions of variable x, then the nth derivative of the product uv is given by u into v, its nth derivative will be un v. Un denotes the nth derivative of u with respect to x, plus nc1 un minus 1 v1. v1 denotes the first derivative, un minus 1 denotes the n minus 1 the derivative, nc2 un minus 2 v2 up to so on, plus ncr un minus r vr, plus up to last term will be ncn u vn for every n belongs to n. So this is known as a product rule for successive derivative. We're going to prove the statement using mathematical induction. We shall prove this statement using PMI. As you know that for the PMI, first you have to prove the result is true for n equal to 1, then you have to assume the result is true for n equal to k, and then you have to prove the result is true for n equal to k plus 1. So this is the procedure or 3 steps which you have to follow for using the PMI. So first of all, let us consider the statement Pn is u into v at n, that is the nth derivative of uv is unv plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus ncr un minus r vr up to so on ncn u vn. This is my statement number 1. To get a result is true for n equal to 1 or n equal to 2, we have to use the definition or a product rule for first derivative. Let us consider a function f which is u into v, where u and v are two functions of x. Now if I take the first derivative with respect to x, we will have u into v at 1, that is the first derivative of that is as per the product rule for first derivative, it is u1, a derivative of u into v as it is, plus u v1, that is a derivative of v, u as it is. And again if I take the differentiation of this, so taking the differentiation again, taking derivative, we get u v2, that is u2v, that is the derivative. So here the product rule for this one we have to apply a v as it is, derivative of u, that is u2, plus u1 v1, that u1 as it is, derivative of v, that is v1, u as it is, derivative of v is v2 plus u1 v1, that is a v1 as it is, derivative of u is u1. Now u1 and u1 will come 2 times, so this I can write down as u2 v plus 2 times that 2 I can write out as 2c1 u1 v1 plus u v2. So hence we can say that the theorem or the result is true for n equal to 1 and 2. For 1 we have here and for 2 we have here. Now let us assume that the result is true for n equal to k. That means u v k, that is the kth derivative of uv, will be uk v plus kc1 u k minus 1 v1 plus kc2 u k minus 2 v2 plus so on kcr u k minus r vr up to so on kck u vk. Now differentiating both sides with respect to x. Why we are doing it? Because we need to calculate the result is true for k plus 1. So differentiating both sides with respect to x, we get uv k plus 1. So kth derivative is already there. We are doing one more time derivative, so it is k plus 1, and we have to use the product rule for this thing, and we know that the differentiation of sum of two functions is the sum of differentiation. So if I use that one and using the product rule here, uk plus 1 v as it is plus uk as it is, derivative of v will be v1 plus kc1 as it is, a derivative of this quantity will gives you u k minus 1. If I take the first time derivative of k minus 1 one more time, it will be k is there and v1 as it is plus kc1 u kc1 u k minus 1 as it is, a derivative of v1 is v2 plus kc2, a derivative of uk minus 1, sorry, derivative of uk minus 2 will be uk minus 1, a derivative v2 as it is plus kc2 u k minus 2 as it is, a derivative of v2 is v3 up to so on. Let us take the derivative of this quantity, that is kcr as it is, a derivative of u k minus r, that is u k r plus 1 vr as it is plus kcr, a derivative of u k minus r, it is as it is, and a derivative of ur is vr is vr plus 1 up to so on. A last term that you will have kck u1 vk, that is a derivative of u is u1 vk as it is plus kck u, a derivative of u into vk. First time we have did for u and now we have to do for vk, u as it is, and derivative of vk is vk plus 1. Now in this you can just observe the two terms which having the same quantity, that is this term and this term is the same. Here this term and this term will be the same. this term and its next term will be the same, this term and its previous term will be the same, and this term and its next term will be the same, and so on. So let us write down this quantities together. This term is alone and the last term is also alone. So by writing this one, what we can say is u v k plus 1 is equal to u k plus 1 v plus inside bracket, you just observe that here it is 1, but 1 I can write down as kc0 because kc0 is 1. So kc0 plus kc1, that kc1 is this one, uk v1 plus a next term that you can observe, that is kc1 plus kc2 and uk minus 1 v2. So it is kc1 kc2 uk minus 1 v2 plus a next term will be kc2 plus kc3, which will be the next term. So it is kc2 plus kc3 uk minus 2 v3 up to so on. Now if we can write down the previous term to this, kcr, or I can write down previous term to this, next term to this one, whatever term you should write. Either you can write the previous term to this term, or you can write down the next term to this one, whatever you can do it. Let me write down kcr plus kcr plus 1. That means what I have written is the next term to this one, that is uk minus r vr plus 1 plus the last term, last term is this kck u vk plus 1. Now we just observe that what is the value of kcr plus kr plus 1. This is k factorial upon r factorial into k minus r factorial plus k factorial upon r plus 1 factorial into k minus r minus 1 factorial. You just observe that k factorial upon r factorial is common out. Also the common thing is k minus r minus 1 factorial. What is left inside? Here the quantity is left is 1 over k minus r, plus here it is the quantity is left is 1 over k plus 1 over r plus 1. If you simplify this, then it will left to k factorial upon n factorial into k minus r minus 1 factorial, and in the numerator it is left with r plus 1 plus k minus r. So you just observe that r is cancelled out, and in the denominator this two quantity is already there, that is k minus r plus 1. So r plus 1 is there, k minus r is there. If you combine the r plus 1 with this r factorial, that is r plus 1 factorial, and k minus r into k minus r minus 1 factorial is k minus r factorial, and in the numerator it is k plus 1 factorial. So finally what we got, it is kcr plus kcr plus 1 will be, you can see that it is k plus 1 factorial, k plus 1 factorial upon r factorial, r plus 1 factorial into k minus r factorial. But this k minus r factorial I may write down as k plus 1 minus r plus 1 factorial. So I have added and subtracted terms here. So this is nothing but the k plus 1 c r plus 1. And it is true for any r which is smaller than k. This quantity is true. So hence we have for first one, it is as it is, the first one. If I call this is the equation 1, then the equation 1 becomes, we have uv k plus 1 equal to uk plus 1 v as it is, uk plus 1 v as it is. Now this is kc0, kc1. So in particular, instead of r, it is, I can say it is, if you want 0, then you can put the r equal to minus 1 here. So this is, so if you want that this result is true, then you can put r equal to 0 here. So it is, so for r equal to 0, you will have kc0 plus kc1. This is k plus 1 c1. R is 0 here. So it is k plus 1 c1 uk v1, which we have uk v1. This is, according to this result, r equal to 1. So it is kc1 kc2. We have here uk minus 1 v2. So that is k plus 1 c2 uk minus 1 v2 up to so on. And you can write down for this term also and this term. Here you have to substitute k is equal to r here. So it is, you have to substitute for that, and we have a k plus 1 r plus 1. We have it is u k minus r v r plus 1 up to so on. And the last term, instead of kck, we know that kck is same as k plus 1 ck, because both this value is equal to 1. So that's why it is k plus 1 ck plus 1 u v k plus 1. And therefore what we can say, the result is true for n equal to k plus 1. You can observe that whenever n is there in our result, we have k plus 1 over there. So therefore the result is true for any n belongs to n using PMI. Let us solve a couple of examples for finding the successive derivative of some function. For example, let us consider y is equal to x square e power x. The question is find yn. That means the nth derivative of x square e power x. As per the rule, what you can have, this is a product of two functions you have. Now, as per the rule, what is u into vn is there. Your rule is un v plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 up to so on. The last term is u vn. Here it is interesting to know that if you want to pick up your u and v perfectly, then the formula we can write down smoothly. See, for example, if I take this is e power x as a u and this is as a v, then it will be beneficial, because a first time it is a v is there, a second time it is v1. So we know that the first derivative of x square is 2x, and third time it will be 2. Second time it will be 2, and third time it will be 0. So what will happen is third term will become 0 here. So it is better that you can choose your, this is as v and this one is as u, as per this formula. So if I apply this Leibniz rule, so applying Leibniz theorem, we have yn, that is x square e power x nth derivative of that un plus nc1. The first derivative of x square, that is 2x, that is u v1, e power x n minus 1th derivative plus nc2, a derivative of x square, that is 2, e power x n minus 2nd derivative, nc3, derivative of 2 is 0, and e power x n minus 3. But the further term is also 0 because the derivative of 0 is again 0. So there is no need to write down the further terms, only the 3 terms will come up here. And we know that the derivative of e power x n times, or successive derivative of e power x, as per the formula it is e power x. And nc1 is, we know it is n, so it is 2n x e power x. And we know that nc2 is n into n minus 1 by 2. And derivative of e power x is e power x. You just observe that this 2 is cancelled out, and if you take e power x common, then the final answer is x square plus 2nx plus n into n minus 1. This will be the answer for x square e power x. Let us do one more example. Let us consider y is equal to x square sin x. Now here again, if you choose this is as v and this one as u, that will be beneficial because first time derivative is 2x, second time will be 2, and the third time will become 0. So as per the applying the Leibniz rule, we can say that this is x square sin x nth derivative of that. That is nc1. The derivative of x square is this 2x, the derivative of this one, that is the first derivative. Then it is sin x n minus 1th derivative plus nc2. The derivative of 2x is 2 sin x n minus 2. Further derivative nc3, a derivative of 2 we know it is 0, and sin x n minus 3, and the further all the terms will become 0. And we know that the nth derivative of sine, as we have discussed in my previous videos, that it is x plus n pi by 2. We have used the formula that if y is equal to sine ax plus b, then yn is a power n sine ax plus b plus n pi by 2. So as per this will be that nc1 is n 2x sine x plus n minus 1 pi by 2 plus nc2 it is n into n minus 1 by 2 into 2 sine x plus n minus 2 pi by 2, and the further term will become 0, and this will be get cancelled out. So the final answer, you can say it is x square sine x plus n pi by 2 plus 2nx sine x plus n minus 1 pi by 2 plus n into n minus 1 sine x plus n minus 2 pi by 2. So that's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.